Good morning and welcome to INDAM workshop on mathematical modeling and analysis of degradation and restoration in cultural heritage. This is the second edition of this event, organized in mixed mode due to the COVID pandemic situation. So it will host online and in-person talks. And it was a pleasure for me to share this experience organizing this event with Cecilia Cavaterra, Margherita Solci, and Michela Spagnuolo. And special thanks goes to the workshop sponsors. And in particular, I would like to thank very much INDAM, l'Istituto Nazionale of High Mathematics, Francesco Severi, for fully financing this event. So a special thanks to Giorgio Patrizio, which is the president of this institution, and also thanks to INDAM staff for their great support in the organization of this event. So Elisabetta Esposito, Mauro Petrucci, and Sabina Delfonso. And so let's go back to the first edition of this event. The first edition that was held in Rome in 2019, and this was the foundation of this kind of workshop was made to create a bridge, a connection, interdisciplinary connection between scientists, professionals, and owners operating in cultural heritage. And the main topics of the previous edition were corrosion and sulfation, chemical and mechanical damage, stress in thermomechanic systems, adhesion and contact problems, phase transition and reaction diffusion models, additive manufacturing, and restoration techniques. And most of the contents of the previous edition can be were collected in the INDAM Springer series volume entitled Mathematical Modeling in Cultural Heritage, edited by Springer with the presence of Elena Bonetti, Cecilia Cavaterra, Roberto Natalini, and Margherita Solci as editors of the previous event, as members of the scientific committee of the previous event. And we also, for the present participants, the volume is here, so you can have a look. And regarding the present workshop, just a look to the program at glance. We are very happy to announce the opening lecture today of Roberto Natalini, Director of Istituto per le Applicazioni del Calcolo Mauro Picone. He will talk about forecasting damage and consolidation, mathematical models of reacting flows in porous media. And we are also very happy to announce the keynote lecture by Ingrid Dobeshi this afternoon. As everybody knows, she is a distinguished professor of mathematics, electrical and computer engineering at the Duke University. And she will talk about X-ray separation and underdrawing extraction. We will also have 8 sessions with the 27 invited talks. So we are very, very grateful to all the speakers and participants that accepted our invitation. And we will also have a roundtable tomorrow afternoon about the impact of COVID-19 pandemic on cultural heritage, from fruition to conservation practices. And on Tuesday evening, for the in-presence participant, we will have a social dinner. This is the program at glance, the schedule. Would like to report that on Tuesday morning, we will have De Filippo presentation instead of Brozzu, as previously declared. And the fact that Francesco Freddi this morning will give the talk online and not in presence as indicated before. The invited talks of the first day are reported here. For the second day, we will have these talks. And finally, for the third and last day, we will have these presentations. All the participants can we will be very happy to have their contribute to the volume of Inverm Springer series of this event. And I underline just that this volume is indexed in Scopus. Finally, just a quick look to the round table. The speakers will be Elena Bonetti, Minister for Equal Opportunities and Family of Italian Republic, Costanza Miliani, Director of Istituto di Scienze del Patrimonio Culturale, Barbara Nazzaro, Architect of the Archaeological Park of Flavian Amphitheater, Austin Nevin, Head of Department of Conservation, United Kingdom, Federica Rinaldi, Archaeologist of Flavian Amphitheater, Maria Laura Santarelli, Scientific Responsible of Heritage Lab of Sapienza, and Maria Giovanna Sarti of Galleria Borghese Museum. And the chair of this event will be Michela Spagnolo, which is the director of IMATI. And finally, the social dinner will be on Tuesday at Restaurant Saporito in Via Tiburtina 140. And as you can see, is quite near from here because it's 1 kilometer on foot. So it would be, I hope, a nice walk from here. And I hope you enjoy the new edition of MACH 2021. Thank you to everybody. And let me introduce Professor Giovanni Naldi from the University of Milan.
Okay, so it's a pleasure for me, also an honor, because the open lecture for these very beautiful workshops, and it's a pleasure to introduce Roberto Natalini, and from CNR of Rome. He's also director of IAC in Rome, but I won't see it. That is the heart, for example, for the MACH, which is a blog, about a site about, I think, enthusiasts and lovers of mathematics, applied mathematics. Okay, and also I want to cite it, and is a director of a journal, OPSA, or the journal, Archimede, for teaching, and also is involved in a committee of European Mathematical Society about the public awareness for mathematics. And also want to speak about the science and comics. Why? But because I think is a right person to open a workshop about that, because Roberto approaches cultural world from different point of view. The instruments, the tools, but also the topics for cultural world. And mathematics is a part of cultural world. And so sooner or later, I will find out how it does all this. Because I guess that the time for any of us is 24 hours. And I don't know why it's possible to do that. I don't know if it's this lecture, because the lecture is focused on the research topics about the reaction diffusion flow in porous media with application to restorations and to other things.
Fine. I was in last week. That's why I couldn't really work on our project till the weekend. I'm sorry. I'm sorry. Yeah.
I was not travel and still I didn't work at all.
Sorry, it's a technical problem, but you know.
So you have a better excuse.
I just caught a head cold and I was knocked out. Yeah.
Somehow we are less resistant.
Okay, so you
The cold already in September.
Yeah, with the first drop of temperatures.
non so come fare.
Yeah, and then of course, Hinek and I had to become vaccinated. That's it.
Okay.
The usual stuff.
I think the best thing is to begin.
So,
Okay.
is life almost back to normal at IAC?
Like I have to use my microphone.
And I was discussing last week to have
Share.
Lambda seminar live hybrid, and there was a small resistance because hybrid doesn't really work, and we are not allowed to go to the lecture
Riccardo
hall.
Rossi lo vedo con l'acceso si legge. Talking GNFM,
And I have
GNFM.
installed Microsoft.
Okay.
Okay, I think so. It's better that Roberto begins.
Okay.
Sorry for this technical issue.
Okay, so thank you very much. So happy to be here in person. Okay, so the idea of this open lecture is to make a sort of panorama of some models, mathematical models we introduced in the recent years, especially two classes of models. So I will be not too specific, not too technical, because also in our audience we have a mixed community, but I have to introduce anyway some equations. So partial differential equation will be shown sometimes during the talk. Anyway, okay, what are some conservation activities which are useful also for mathematical modeling? First of all, understanding what happens to cultural heritage. What are the mechanisms acting on stones, wood, iron, and so on. And then another activity which is much more mathematical, in some sense more scientific, is to forecasting and preventing damage and degradation. We know after Cesare Prandi that in some sense any cultural heritage is a sort of the end of its history. So I mean, the degradation in time is, in some sense, a part of the history, but we want to preserve, to keep these monuments for future generations. So it's important at least to know what is going to be in the future. And so the idea is to improve conservation by some actions like cleaning, consolidation, treatments, and so on. And one particular goal, which is not really addressed in depth with the mathematical tools, is optimization of intervention, because we have a limited amount of money to spend to the conservation of cultural heritage, but we have to choose what to do and to plan our action in time. Mathematics is a discipline to do that, is a tool to do this kind of optimization. And also another topic which is really important for our country now is sustainability of tourism and the fruition, the clever fruition of the monuments, preserving the environment, the integrity of the monuments. And I think that that's very important. Okay. Our new key tool here, a lot of us, we are introducing this field as modeling and simulation, which is still in the beginning in some sense. We started some years ago to work on these topics, but still there is a lot of work to do. and I will show what kind of problems we can attack with this kind of agents. Now I apologize because a lot of people already assisted to my talks in the past, and a lot of slides are coming back to in this talk because I collected some pictures I loved and motivated my research in this topic. Here, the picture taken by the book by Winkler is from a case in Westphalia, and they are the same statue at the beginning of the century, and I mean 1969, and this statue was 200 years old, and so there is some damage. Okay, thank you. Great. 200 years old, and this statue was with some cleaning was necessary at the beginning of the century, and after 60 years it was completely, dissolved. And there's this sentence from the Environment Protection Agency, American Environment Protection Agency, ancient buildings and sculpture in a number of cities, and whether more during the last 20 years than in the preceding 2000. So the situation, even if we have a diminution of pollution in Italy, for instance, in Rome, we have still this kind of problems. And another example, that's Bassolino in Venice, and from 1978 to 2007. Here I have an echo, I don't know why. Anyway, you see the degradation, we lose all details. And this kind of weathering is what we are going to study to try to understand, to provide at least some tools to forecast what's happening in the future. Okay, what's the current tool? There is a plan of risk from the Ministry of Cultural Heritage, Cultural Heritage, and the statistical tool, which was quite classical, is the Lippert formula, which is just a sort of standard of regression, where you have the loss of material in time. And maybe you have to close all the microphone in the other buildings, not in mine. And so you see this formula is quite simple. You have some constants. Okay. I have to speak in the microphone, maybe it's better. So here, maybe I have to close this microphone, I don't know. I'm learning, sorry. I'm quite slow. It's a slow learning curve. Anyway, I don't know why now we are not full screen. And so this Lippert formula is just taking into account some, I don't know, rainfall quantity, SO2 deposition, and so on, velocity and concentration, and so on, some factors. You see that there are some mysterious constants which are derived by the campaign across Europe during 8 years. So that's just an average. Okay, clearly we have some local phenomena occurring here, but the same constants works everywhere. So if you have the same condition, you have the same result. But we know that this formula cannot work for calculations. It works for, I don't know, an estimate of renovation of buildings, civil buildings, in a country. So just an average forecast of what you are going to spend money to make renovations. But here you see Rome, and you have two that's the central wrong of Piazza Venezia, and Palazzo Chigi, the top corner on your left. And here there is Colonna Antonina, and here Colonna Traiana. And you see the columns are really some 100 meters apart, but they are in a very different state of conservation. A lot of works of conservation were made on the Antonina column some years ago, but still, the preservation of Colonna Traiana is incredible. The details of sculpture are amazing. I had the opportunity to go up on this column to see from a few centimeters the details of the sculpture, and still well preserved. Why? And from the formula, it's impossible to understand the situation. So we have to understand why the microclimate is important, why the north face of the column or the top of a building is different from the bottom and so on. So we have to model the situation with other tools. And the modeling approach, so it's similar in degradation. So collect the main factors of degradation, write down the main chemophysical relation by form, and extract the main information from the model and build up a simulator, numerical simulator to try to extract the, I don't know why it's, okay. So you have the building, the equation, and the simulation. So that's the process we are going to address today. And we have maybe two different kind of models. The surface deposition, when you have a surface, you have some, some rain, some humidity, temperature, pollution interacting with the surface, or capillary penetration from some source, where I don't know, maybe a building, a wall of a building, or bricks on the ground, and you have the capillary penetration of water. Okay, so the first part is recall what the model. Maybe you know that a lot of talks in this workshop will address this kind of model. So I try to give a sketch of what are the ingredients of these models for this surface damage. So we have some facts. You have the concentration of pollutants, turbulence, rugosity. Not all are already included in the present models, so that's challenging for the future. And chemical affinity. SO2 reacts with calcium carbonates, and this is completely different on silicate and so on. Humidity, and there are a lot of pollutants. SO2, for instance, is the most aggressive, but also you have the NOx and carbon dioxide, which is now rising in the atmosphere, and so that's a crucial point to address. Was the new contribution to damage. And for instance, if we take just sulfation as a action, we have the reaction of SO2 with the calcium carbonate, you have production of calcium sulfate, and the new layer is going to melt faster than the marble, for instance, of traversing and so on, and it's more fragile. So, we have to study and essentially start from this one. Here there is an experiment made by many years ago by Roberto Natalini in Rome. Here you have a layer produced in the lab of Sapienza after an exposition of 7 days to full concentration of SO2, 100% of humidity. And you have this layer, which is, you see, there is a thin front between marble and gypsum. And this part is completely inhomogeneous, and this grow up on the boundary. And so what we want to understand is how to study this kind of crust. But the idea is that all all other models for other kind of crust, other kind of interaction, which you first can build by the same approach. I mean, here I described what we did, but the same model can be adapted to different situations. And here, that's the idea. So the simplified view, we have air with pollutions, and here we have a crust of some layer, external layer. Maybe, for instance, we have seen for, I anticipated, but for metals, we have 2 layers of different materials. And here we have the stone, the pristine material, which is at the end. And so you have diffusion inside and then the reaction here when you get the new material. And here, this crust maybe is mixing of different components. Maybe it's not pure gypsum or pure crust, but there are still elements of the original stone. And here, what we can see at the microscope is again by courtesy of Roberto Natalini. And here we have this growth, and you can see that we have a progression, a growth in time, and we want to understand what's the speed of this growth. And that's the typical question mathematicians address. I remember in the beginning, when I started to study these kind of topics, I was quite surprised that people didn't ask these kind of questions. So what's the speed of growth? There are some statistics like, okay, we have seen that a paper that some monuments in Milan was polished some years ago after 50 years of exposition, and they found 50 microns of crust, and they, okay, 1 micron per year, but that's not the real speed, that's measured speed. And so understanding what's the real speed of growth of this crust is crucial also for restoration practice. And now I have a lot of slides, so maybe I can go faster. And the idea is to build this kind of model. So you have to write balanced laws, which are physical balance laws. So we have something's changing, the concentration of, I don't know, SO2, calcium carbonate, gypsum, and so on. And you have here there are some quantity which are gases or liquids, air or SO2, for instance. And here calcium carbonate and gypsum are static; they don't move, so there is no spatial movement. Here there is a flux. We have to understand, and the reaction terms. The reaction terms are classical. You have just a kinetics, 2 molecules of, I don't know, SO2, 1 molecule of SO2 or 1 molecule of calcium carbonate are meeting. You have some weight given by the molecular weight of the single molecule and the reaction rate, and you have the kinetics. And so, I mean, there are some, you can measure this kind of ingredients, and you can write these laws. But what are the interstitial velocity of SO2 and the evolution of concentration is a matter of modeling. And we are lucky that there is a lot of history about these models for oil recovery, for instance. And so we can adapt. Even the scale of this kind of models is completely different. And here you see that you take porosity. Porosity is very confusing tool. Porosity does not exist because if you are, I don't know, an atom, you don't see porosity because you are inside of the atom, or there is nothing. So there's just 0 or 1. But in average, in the intermediate limit, when there is some stability, so that's the volume of void divided by the total volume. So it's a macroscopic idea. Porosity does not exist, and it can change even in the same material. And here there is a sort of derivation, but the idea is that's a linear quantity. I mean, the volumes are just the sum of volumes, so that's derivation. So if you have a mixing of, I don't know, in this case, marble and gypsum, it's just proportional to the quantity of marble and gypsum. So that's it's linear in this case in the quantity of calcium carbonate. And that's all we know to retain from this analysis. And then we have to introduce the porous concentration, because the physical laws are written usually for an homogeneous medium. But you are in the porous, you have to restrict your attention. I mean, if you have the concentration for a volume, you have to be in the void, I mean, in the part where it can flow. So here you take the concentration, the porous concentration is just the, I mean, such that the total concentration is a porosity times the porous concentration. So you define this porous concentration, thanks to porosity, and again, from the interstitial velocity, you can find the seepage velocity, which is the velocity inside of the pores by averaging this kind of quantity. So you restrict your attention not to the full volume, but just the part of the volume where you can find some flow, because otherwise in the submetrics you can pass. And that's the one difficulty. So you can write down the equations, which say just that SO2 is flowing inside of the porous medium and reacting. Air the same, but air there is not a lot of reaction, and the marble is changing. You can eliminate the gypsum because just by the conservation of the mass, yeah, the equation is already satisfied, and you can derive thanks to two physical laws, which are Darcy law and Fick law. You can derive the equation for the velocity, the seepage velocity, the total velocity of the fluid, and for the difference, I mean, of velocity of the SO2 and the total velocity of the mixing. And so you have by Fick law, you can address this kind of diffusive velocity of what's the movement of the molecules of SO2 inside of air. So we have this kind of equations. This is a rigorous derivation made in a paper with Giuseppe Ali and Isabella Toscolo some years ago. And we write the final equation, and that's the final system for any quantity. I mean, here you can replace SO2 or calcium carbonate by other quantities just by changing the reaction terms, because the other quantities are the same for every medium we are going to consider, any kind of stone, any kind of pollutants. And here just to focus. And the problem here is that how to determine the pressure. And that's an old problem, even in fluid dynamics. And Navier-Stokes, Euler, and so on come from just the consideration what is pressure. And we have two possible choices. One choice, which is not really explored, fully explored. We wrote a paper about that, but I mean, is for medium where we have a lot of permeability, like travertino, for instance, but we didn't apply a lot. Just you close the system by taking the fact that in this limit, the air is constant. I mean, the medium is not changing. So you can eliminate one equation and you find an parabolic elliptic system with one ordinary differential equation, but this one is elliptic for the pressure and you can close the system. But if you take another idea, I mean, for marble, where permeability is absent, you just can assume that the permeability is zero. You have this in this case, you can eliminate pressure. And here you have this system which was introduced previously with Denise Alequadrione and Fasmadiere in 2004. And then it was the basic for many other models that we developed during this year. And so you have this layer forming, and here the marble, as I presented at the beginning. So for marble, this kind of model is much more effective. And another possibility is to take the limit when the kinetic reaction goes to infinity. When this term A is the first reaction limit, when A goes to infinity, you can recover a Stefan problem where you can include other phenomena like humidity, swelling, because the volume of gypsum is different from the volume of marble, even with the same quantity of molecule. And here you have these layers, the thin layers, which are quite, I mean, in a fast reaction limit, you are just eliminating this transition, this mushy region between the two different materials. So you assume that you have marble or gypsum and air, and they are separated, and you can forecast something about it. It's easier to be studied in the limit, and you can prove or even mathematically that the evolution is like square root of t according to the square root of the external concentration of SO2, for instance. And this kind of evolution, so it's not linear. So 50 microns on 50 years, so it's not 1 micron per year. Square root of t means that in the first 2-3 years, you have most of the growth of this crust, and then you stop more or less. You have the passivation of the crust. That's a technical term because it was already observed. But here we can quantify this kind of behavior. And here there's a plot of experimental data from the experimental lab and in the square root of time scale. And so you see the agreement with the numerical experiment. So, I mean, it's quite effective. We prove it also in situ with some campaign of Vittoriano Rome some years ago. And then we want to go forward. What are the other directions that we move? Recently, with Cecilia Cavaterra and Bonetti from Segregazione and Francesco Freddi, we tried to add some feature to this model. For instance, rugosity, because here you see 3 kinds of marbles treated by sandpaper of different granulosities. So you find here 180, 240, 220. And it's completely different. The surface you are observing. And so that's from a paper about this kind of study of environmental science. And so you ask, what is the behavior of this surface when you have a different granulosity? So we introduced a model where we covered the previous model, but with the rugosity term, which is just acting on the surface. This rugosity is a quite complicated idea because it's very difficult to measure rugosity. You ask a physicist, there are different definitions. There is a roughness, rugosity, and also the tools. It depends on the tools you are using to measure this kind of quantity. But anyway, this idea that your surface is going to be more complicated, and so in some sense, what you expect that the absorption of the pollutants is different, but there is a limit when maybe it is too intricate and so too complicated to is a sort of filter. So I mean, we need more experimental work, but still we modified the surface, the boundary condition according, so the permeability depends on this velocity. And so what we found is a different behavior according to the different behavior of this permeability with respect to rugosity, if it's a linear or a quadratic interaction. We have different evolutions in time, but still we need more data, more experiments. And that's the question for people doing experiments on materials to work on this topic. Another idea is the thermomechanical models. I mean, we introduced something which is the internal state of damage. I mean, 1 if it is intact, 0 if it's broken, the stone, and you introduce some relations, some equations to say the mechanical state of our specimen. Here, for instance, that's a test on a marble prism, and you have a stress applied on the top and the bottom, and you have here a sort of notch to start the damage, the fracture here in this part, and you apply this stress for some times, no stress before sometimes 0.7, for instance, and then you have a linear stress, and then you have a constant stress after this time. And you see that really we have at the beginning nothing happens, just we have the evolution of crust, but there is no damage. But then after this time you are applying the stress, we have this kind of damage evolution, which is very fast. So we have a coupling, and a linear coupling between these two different phenomena. Here, there's the change in gypsum and there's SO2, and here the change of gypsum. So according to this kind of nonlinear behavior, it's an acceleration of that damage flow. The second part, I don't know, I'm sure that. Okay, is a resin lamp experiment. You take a brick, you put this brick in water, and you have this resin damp because capillarity. And after, I don't know, here I can see 5 minutes, 18 minutes, 64 minutes, and so on. I want to understand this kind of phenomena because they are typical of what happens when you look at a lot of monuments, building, artifact, cultural heritage. And you know what I need to do is this noise. Okay. Here we want to assume that we have a macroscopic approach. Clearly, we could try to follow the single molecules inside of the pores and so on, but we don't know the structure. So again, we have to rely on a macroscopic view because that's easier to be measured, right? And so we introduce a balance equation as before. So I mean, the ideas are the same, just we have a different environment. And so we have here the density of water, which is constant. And that's theta L is the fraction of volume of the pore occupied by the liquid. Theta G is the fraction of volume occupied by gas. So you have here, you have the pores, and you have a mixing. Sometimes you have just a liquid, sometimes you have a liquid and gas, for instance. And the V is the flow in the porous matrix. So it's some sort of measure of what is passing really, the quantity of material passing inside the pore for unit of time. And then we have a term which is evaporation, which is, we are not speaking about that, but usually when you have a real break, a real wall, you have to consider that there are some surface where you have evaporation, so you have to take into account in your equation. And so, how do you find the fluid velocity? So the total porosity is given by, because by definition, it's just the sum of the fraction of the liquid and the fraction of the gas. And so that's because otherwise there is the porous matrix. And again, you assume the Darcy law. So you have the pressure gradient, the permeability, and the viscosity of water, which is known. And so these two terms are crucial. And they are characteristic of the material on one side, but also of the liquid you are using. Right? For instance, you have no water, but you have I don't know, white spirit, because you are introducing some consolidant, as you can see later. And so it's just a mixture of white spirit and water entering inside of the pore. So I mean, this relation can change. And but essentially this part is the liquid, and this part is due to the geometry of the material, the so-called permeability, which is can be a matrix. So here we are assuming a scalar, but it's much more complicated than that. And the capillary pressure depends on the fluid saturation here. Here are the curves for the relative water permeability, for instance, also the gas permeability, the other medium. And we used some kind of loose formula, just a polynomial approximation. But the main point that you have to retain is the fact that for very under a threshold, you have nothing. I mean, you have no capillary rising, so you have just nothing happens under, for instance, 0.2, something like that. That's from the books, but so that's a classical value. So 20% of humidity inside of the pore, and then you have this growth. On the other hand, the shape of capillary pressure comes just from experimental curve. There is no theory of that. You can, there are some people trying to understand that for a single material, but it's very difficult. And also from distribution of pores, it's difficult to derive the real shape of this curve. And so the capillary pressure is usually infinite when you have this threshold, the same threshold for the starting of the capillary raising. And usually you have different curve from absorption and drainage when you are emptying your pores. So you have some hysteresis here, but you have to see now just the capillary raising. And for instance, this kind of formula can be used, just a phenomenological one. So you have some parameters to be fitted. Here I'm cheating because usually we use Gabriella, Bretti, we use a very simple formula, even simpler than that, because it's very difficult to deal with this lot of parameters. But the main idea is that if you have just water, nothing is happening, porosity is constant, no evaporation, and so you can concentrate on S, which is, if you remember, porosity, that's the theta L divided by the porosity. So that's the quantity of lipid, the fraction of lipid. And so you have just this kind of equation, and you can find a function which is just given by this product between the derivative of the capillary pressure, the porosity divided by the viscosity. And so the problem is that usually, if you take this assumption that these functions are not regular, and you don't know what's the threshold, so you are in this situation, and you don't know what S naught is, and what you do, you have to assume something. In this case, that gamma is greater than m over n plus 1. Otherwise, this function is not well defined. If you want to have this function is 0 in this part, because you want to run a code to fit this kind of calibration, you have some analytical condition. But I mean, finally, using, I mean, even other kind of approximation, even simpler with a simple parabola or something like that. In fact, this B function can be just a cubic if we want. And it's possible to have a good fitting for some materials, and it's still it's a work in progress, but we have obtained some results. Maybe somebody will speak about that during this workshop. And so we have, so that's the first ingredient. The other ingredients, because we are speaking about a reaction, flows media, it's the fact that some chemical component is flowing. So this chemical component is, we have a speed which is given by the speed given by the water. But also there is a diffusion of this, as previously, you remember, for the pollutants inside of the surface models. Even here we have a diffusion of the pollutants inside of the water, and we have the reaction term, and which is characteristic of this kind of problems is the fact that the porosity is not fixed. Porosity is changing during time. This is difficult to deal, especially from the analytical point of view, because all the theorems of regularity we have to prove again by using other techniques, because usually they are not satisfied by this kind of changing porosity. Okay, an example is the transportation of consolidant a consolidant, which is usually is a sort of material, a chemical component you add to with the water or white spirit inside of a material to try to improve the strength of the material. So if you lose, you have some powdering of the surface, you see some damage, you try to consolidate. So you have to make an impregnation of this kind of material inside of the stone. But it's not easy. Here, for instance, is a marble with an in-depth treatment with epoxy resin. And you see that's very difficult to have an effective penetration of this kind of material. And sometimes you have even some drawback in the sense that here you have detachment of the external layer, because the mechanical properties of the external layer are different from the inside properties. So after consolidation, you have even worse, you have exfoliation and so on. So one idea is to use ethyl silicate, in particular TIOS, which is this sort of tetratrain orthosilicate, which is quite, well known. And we assume that we have constant density of the fluid phase. We have HO2, because in presence of HO2, you introduce with white spirit, but when a molecule of ethyl silicate meet water, they start to make polymerization. So you start with monomers and you find long chains, which are going to sort of create a rope inside of the porosity matrix. And so to link all the parts of the material, so to try to reconstruct the porosity matrix. And you can write the equation. So we have all the ingredients now. That's a note work with Fabrizio Clarelli, Carlo Nietzsche, and Mariano Santarelli. And here, the first equation we already know, it's the equation for in this case water. We have this part water, or anyway maybe a mixture of water and white spirit. Here we have the concentration of this ethyl silicate, and here the reaction of porosity, which it changed because we have one part. You have the growth by changing for the influence of the liquid, but also if you have not enough porosity, you are losing because you have no space and no reaction. And so there are two different terms, and you have to balance between these two terms. There is nothing if you have no liquid, because you have no silicate, but you have too much liquid. In some sense, this you stop the reaction because you have no place. The experimental fitting is quite good. We did many years ago on some tuffo stones, and we tried two scenarios. The idea is why we want to model these kind of problems, because you can try to different mixing. For instance, ethyl silicate, the ratio between ethyl silicate and white spirit can be 70-30, or the opposite, 30-70. And you have a different shape. For instance, in the first case, you have a lot of penetration, but there is too much ethyl silicate. So, in some sense, you have the impregnation is not in depth, because the porosity here there is a peak, here is more smooth. So maybe according to what you want, it's just an example, you can change to obtain different results. Maybe you want to be in depth inside of the stone, or you want a good consolidation on the front. So changing this, but usually it is not done, because you just buy your ethyl silicate in the first mixing, 70-30. So that's other approach using the same model. Maybe other people are going to discuss these kind of topics. Self-crystallization and inhibitors can be modeled by the same kind of arguments. treatments to make the surface hydrophobic. That's another line of research. And also the reaction with the CO2 and other pollutants can be involved by using the same equation, just you change the terms you're using. Other situation, for instance, we have a biofilm damage, and other models we built up with Magari many years ago at Seglarelli, and more recently the same line, really different from by damage, but similar to what we did with salt crystallization, the iron stains inside the porous stones, Gabriella Bretti and the group in Sapienza, Rita Reale, maybe she's, I don't know. And we obtained some results. Why this? That's like coffee stains. You see, here you have a ring, and inside you have the stain is weaker than on the border. So that's clearly a quite strange phenomenon, and we wanted to understand this kind of phenomena by mathematical methods. In conclusion, I think that's this panoramic view can prove that it's possible to design this model to take into account mechanical, chemical, even bio damage in porous media. Clearly, we need experiments. Without data from experiments, interaction, we have to design experiments together with people, chemists, or people expert in restoration, because otherwise we are stuck. We don't know what's happening. And my feeling is that we are at the beginning of a field. I mean, we have a few results, we have few evidence that this kind of project works, but still we know very few topics, and I think that this kind of workshop are useful to improve our knowledge, our horizon, and to progress in this kind of topics. So I have to thank a lot of collaborators in this kind of because I did all this stuff not alone really, but there's a group in my institute. I want to thank. Maria Laura Sateri was a support for 15 years in this kind of works, because I learned a lot of topics in conservation just discussing with her, and a lot of collaborators in a list, mixing list, but we worked a lot, but not enough, because we can work more. So I hope that that's stimulus this workshop and this conference for continue this kind of works. Thank you very much for your attention.
Okay, thank you, Roberto. And only a warning, if you want to hear in person, do some questions, please have to be close here. Okay. And I have a lot of questions about the time. Because
we start late.
It's a stupid one. Is a stupid question, because I think at some moments you say that there is dynamics of the interface is like more or less as a square root of t.
Yeah.
Okay, is it related to some variant solution of porous media equations, or you have a reactions, or probably
no, not really. I mean, okay. Square root of t is just integration.
Yeah.
Okay. So when you have the linear behavior, you have square root of t. So probably it says just that for the surface reaction, the linear regime is quite realistic. It is not the same for the second part, where we have a full nonlinear diffusion, which is even completely degenerated in interval. So also from an analytical point of view, we have no existing emitters we are working on, but I mean, it's still a problem for people in analytics problems. It's just an idea. In this case, we have no estimates of the speed of the propagation. So, I mean, it depends on the materials. So, in this case, maybe when we are in non-degenerate case, I mean, the border or between the threshold and inside the region, we have a polynomial behavior just in this part. Maybe in this part we can have some sort of parameter behavior. But it is not clear because when you reach saturation, you change again your behavior. So you come back to the linear behavior. So maybe on the front you have something, on the front you have a bar, but inside you have the integration. So it's a mix, it's not clear.
Okay, and because for the time, because you show something which is during many years.
Yeah.
So the degeneration in many years. The experiment is some hours.
Yeah.
And I think there is a multi-time. I mean, there is a first something because if you wait so many years, what predict the model? I mean, because in some sense there is some saturation with something which is lower of
To be clear, when you use just the linear model, I mean the surface reaction, in this case, you have just the behavior of the Stefan problem. The Stefan problem, the behavior is square root of t. Square root of t means that the velocity 1 over square root of t. So at the beginning, you have a very fast growth, even infinite growth. But after some years, to change, to gain 1 micron, you need, I don't know, 20 years. Then at the beginning, it was 4 microns per year. So you have a decay, and you can assume also a stationary solution. That's why sometimes when you have a cleaning, the surface, you have to be careful. And so that's an indication, because if you the raw material, if you recover the raw material by cleaning up to the material, the stone, the original stone, you start again with a very fast. So to keep some layer outside, maybe is an improvement, protection. So it's an indication. But I mean, the idea is that anyway, is like in biology, when you have no time behavior of I don't know, a biological population, you know that you have extinction. At the end of the time, you have extinction all the time. This is the same for monuments. At the end of the time, you have complete damage of the structure. So.
There is some question here or online before, because I have another question and I want to wait for it's a curiosity, not only for you, but for people here. Exists some kind of tomography in order to understand what, because okay, I see the moment I can estimate the crust, but there is some non-invasive experiments in order to understand using, for example, I don't know, using the flow of something in order to understand where is the interface now between stone and crust.
No, up to now, all our techniques to assess the damage are invasive, and get clearly some, I don't know, X-ray, TC scans can be used, but I mean, synchrotron, but I mean, you cannot take monuments, Pieta, Michelangelo, to put in the synchrotron. So, I mean, usually that's very difficult to assess the state of the material. And that's one of the problems, also one of the use of the movements, because you cannot measure by captors the situation, environmental situation. And so you can say, okay, I made a campaign in lab, in situ, with the specimen around the monuments with the same material. And so you can try to say, okay, we have an estimate what is happening inside. But it's very difficult this kind of, you can make a hole, but you can destroy the monuments.
No, okay, no, but not in Brazil, because I think.
Yeah.
Come here.
Thanks, Roberto, for the nice talk. Where should I go?
Here there is a map.
Okay.
Here there is a map. So me send back to the. It's very complicated.
Yeah.
Thank you for the introduction. Thank you, Roberto, for the nice talk. I think it's I have a lot of questions, but there's an appetite for the discussion. I have a mean question to ask, a bit connected to what you were saying. These are super long processes we are talking about, and people take pieces and mean and they do this accelerated sulfatation, carbonation, and so on. And your models, I guess, are fine-tuned to mimic what happens in the lab. Okay, but then what about the reality? So is there a chance? Okay, you my question.
I have the answer. Okay, I mean, it's a nice question, and that's why we conducted a large campaign on Vittoriano in Rome, where we compared the lab situation with the in situ situation by putting a lot of specimens of different kinds of stones, essentially Carrara marble and Monticino marble, near the model. So we have a big rack for 1 year and a half. So we have a comparison what happens at the same specimen in lab that was made by Bretti and by Santarelli, and with the Institute of Conservation Cultural Heritage, the IAC-CNR in Rome, called Vittoriano. We compare the behavior. And the idea, we want to find the same coefficient, because here the pollution, rain is different in the two environments, the humidity, but fitting with the same, with the same constants, the model lab in situ was consistent, with the one difference that the damage in situ, the reality, was a bit faster, because probably there is a catalytic action of some particulates, some metals, some NOx. We don't know, so we are investigating this point. But it is not the error you commit by calibrating the model in lab and using in situ is a small anyway, 10% for instance. But so for a large time it's okay. But if you want to see why it is faster, so to prevent what happens in the reality, we have to investigate this part. That's part of our ongoing investigation. So, but it's a relation, it's not complicated.
Okay, some other questions online? No? Thank you again, Roberto. You have some delay, but try to come back in 20 minutes, okay? Yeah. Because not to add delay to delay. Thank you.
So we start again, huh? No,